Gravity is not a rope pulling objects together. It is not an invisible force reaching out through space. And it is not a mysterious push coming from below, but a fundamental property of reality that determines why matter clumps together, why planets orbit stars, and why the universe has structure instead of collapsing into chaos. At first glance, gravity seems simple and obvious because we experience it every day when objects fall to the ground or when our bodies rest firmly on the floor. But in reality, gravity is one of the deepest and most puzzling phenomena in physics. If you like similar educational content, please like, subscribe, and share the video with your friends. It feels strong, but it is actually the weakest interaction in nature. Gravity acts on everything that has mass, every atom, every stone, every human body, every planet, every star. Even you exert gravitational influence on the entire universe around you, but your mass is so small that the effect is impossible to notice. What you feel as your weight is not the Earth pushing down on you. It is your natural tendency to move toward the center of the Earth while the floor resists that motion. If the floor suddenly disappeared, you would begin accelerating downward, not because something pushes you, but because gravity defines how objects move in Earth's presence. Gravity never disappears. Far from planets, it becomes weaker, but it is always there. That is why planets do not drift away into space. That is why galaxies remain bound together. That is why stars can form from vast clouds of gas. Gravity has one unique property that no other force in nature possesses. It only attracts. It never repels. Electric forces can cancel out. Magnetic forces can push apart. Gravity always adds up. Every mass contributes. That is why, despite being incredibly weak on small scales, gravity dominates the universe on the largest scales imaginable. For centuries, people believed gravity was simply a force acting between objects, similar to pulling or pushing. But that idea was only the first step, because gravity is far stranger than a force. Gravity is not something that acts inside space. Gravity is something that shapes space itself. To truly understand gravity, we must stop thinking about invisible pulls and start thinking about the geometry of reality. Because gravity is not about objects being dragged together. It is about how space and time behave in the presence of mass. And this realization leads us directly from falling apples to planets, stars, and the structure of the universe itself. For most of human history, gravity was understood only as something local, a force that made objects fall to the ground and kept people from floating away. But no one connected this everyday experience with the motion of the moon or the paths of the planets, until Isaac Newton realized that these were not separate phenomena at all. Newton's key insight was simple and revolutionary at the same time. The same gravity that pulls an apple toward the ground also governs the motion of the moon around the Earth. The moon is not being held up by anything. It is constantly falling toward Earth. It just moves sideways fast enough to keep missing it. With this idea, Newton unified Earth and sky under a single principle. He showed that every object with mass attracts every other object with mass, and that the strength of this attraction depends on how massive the objects are and how far apart they are. This meant that gravity was universal. It acted everywhere. On Earth, in space, across the entire cosmos. Thanks to this law, scientists could calculate planetary orbits with astonishing accuracy, predict eclipses years in advance, explain the tides in Earth's oceans, and even discover new planets by noticing tiny irregularities in known orbits. Gravity became a mathematical tool that could predict the future. Yet Newton's theory carried a strange and troubling implication. Gravity acted instantly. According to Newton's equations, if the sun were to suddenly move, the Earth would immediately feel the change, no matter how far away it was. This suggested that gravitational influence traveled infinitely fast. At the time, no one knew why this should be possible. But the theory worked so well that the question was mostly ignored. Over time, small discrepancies began to appear, especially in regions with very strong gravity or very precise measurements. The motion of certain planets showed tiny deviations that Newton's theory could not fully explain. These errors were small, but persistent. They hinted that Newton's description, while incredibly successful, was not the final word. Newton had not been wrong. He had been incomplete. His gravity described what happens, but not why it happens. The deeper cause remained hidden. To uncover it, physics would have to abandon the idea of gravity as a force acting across empty space and ask a much more radical question. What if gravity is not a force at all? What if space and time themselves behave differently in the presence of mass? That question would lead to one of the greatest revolutions in science. And it would come from a single person who changed how we understand reality itself. At the beginning of the 20th century, Albert Einstein realized that the real problem with gravity was not mathematical error, but the assumption that gravity was a force acting across empty space. Einstein asked a different question. Not what force mass exerts, but what mass does to space and time themselves. And the answer was radical. According to Einstein's general theory of relativity, mass and energy do not pull on objects directly. Instead, they curve space and time, forming a four-dimensional structure known as space-time, in which everything in the universe exists and moves. Space is not rigid. Time is not constant. Both respond to mass. They bend. They stretch. They deform. A planet does not attract objects like a magnet. A planet warps space-time around it. Objects nearby simply follow the straightest possible paths through that curved geometry. What we perceive as gravitational attraction is actually motion through distorted space-time. This explains something deeply counterintuitive. Astronauts in orbit are not free from gravity. Gravity is still strong where they are. They feel weightless because they are in continuous free fall, moving along curved paths around Earth without ever hitting the surface. Weightlessness is not the absence of gravity. It is perfect gravitational motion. Einstein's theory also solved Newton's greatest flaw. Gravitational effects do not propagate instantly. Changes in mass and motion travel through space-time at the speed of light. Gravity became dynamic, finite, causal. The theory predicted astonishing effects that Newton's gravity never could. Light bending near massive objects. Time running slower in stronger gravitational fields. Clocks ticking at different rates depending on altitude. These are not thought experiments. They are measured realities. Without correcting for gravitational time dilation, modern satellite navigation systems would fail within minutes. Gravity, in Einstein's view, is no longer about falling objects. It is about how time flows differently across the universe, how space itself changes shape, how reality responds to mass and energy. The more compact and massive an object becomes, the stronger the curvature it creates. Push this far enough, and space-time folds in on itself. This is how black holes are born. Regions where curvature becomes so extreme that the known laws of physics break down. Einstein gave us the deepest description of gravity ever created. But his theory also revealed its own limits. Because at the smallest scales, gravity collides with quantum mechanics. And there, our understanding collapses. When enough mass is compressed into a sufficiently small region of space, gravity stops behaving like a gentle curvature and becomes an overwhelming distortion of reality itself. At this point, space-time bends so intensely that nothing can escape its grip. Not even light. This is how black holes are formed. A black hole is not an empty hole or a tunnel through space. It is a region where space-time is curved so extremely that all possible paths point inward. Most black holes are born when a massive star exhausts its fuel, collapses under its own gravity, and nothing remains to stop the implosion. The boundary of a black hole is called the event horizon. It is not a surface. It is not a wall. It is the point beyond which escape is no longer possible. Crossing the event horizon does not feel dramatic at that exact moment, but once inside, the structure of space-time changes completely. Directions that once pointed through space now point through time. Moving outward becomes as impossible as moving backward in time. Gravity here does not pull harder. Reality itself allows no alternative path. Gravity is not only static, it can move, it can ripple. When massive objects accelerate violently, such as when two black holes spiral into each other and merge, space-time itself begins to oscillate. These oscillations propagate outward as gravitational waves, traveling across the universe at the speed of light. They are not waves moving through space. They are waves of space. When a gravitational wave passes through Earth, it slightly stretches and compresses space-time, changing distances by amounts far smaller than an atomic nucleus. Yet modern detectors can measure these changes, allowing humanity to sense cosmic events billions of light-years away. This was the first time gravity was observed not just as an effect, but as a dynamic phenomenon. The universe became audible. The detection of gravitational waves confirmed Einstein's theory with extraordinary precision, but it also revealed something unsettling. Inside black holes, mathematical descriptions predict infinities, points where density and curvature become infinite. Physics breaks down. Equations stop making sense. These singularities mark the boundary of our knowledge. They show where general relativity collides with quantum mechanics, two theories that work perfectly on their own but refuse to merge. And this collision reveals a deeper truth. Gravity, the force that shapes galaxies and controls time, is still not fully understood. And its greatest mystery lies not in what it does, but in what it truly is. The deeper physics explores gravity, the more uncomfortable a fundamental question becomes. What if gravity is not truly a fundamental force of nature, but a large-scale effect that emerges from something even more basic? In modern physics, there are four fundamental interactions: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. Yet gravity stands apart from all the others. It is extraordinarily weak, impossible to describe cleanly using quantum mechanics, and mathematically incompatible with the theories that successfully explain particles and forces at the smallest scales. This strange behavior has led many physicists to suspect that gravity may not belong in the same category as the other forces at all. One leading idea suggests that gravity is emergent, meaning it appears only when many degrees of freedom act together, much like temperature or pressure emerge from the motion of countless particles rather than existing as fundamental properties themselves. In this view, space-time geometry is not the cause of gravity, but a useful description of deeper informational processes. Gravity would not be something space does, but something that appears when reality organizes itself at large scales. Adding to the mystery is dark matter, an invisible component of the universe that does not emit or absorb light, but reveals itself through gravity. Galaxies rotate too fast for their visible matter alone to hold them together. Either vast amounts of unseen matter exist, or gravity behaves differently on cosmic scales than our theories predict. Both possibilities challenge our understanding. Both point toward missing knowledge. Despite decades of effort, no theory has yet succeeded in unifying gravity with quantum mechanics. Every candidate theory, whether based on quantum gravity, strings, loops, or holography, remains incomplete or untested. This tells us something important. We are not at the end of the story. We are somewhere in the middle. Gravity today allows us to predict planetary motion, detect black hole collisions, navigate spacecraft, and measure time itself with astonishing precision. Yet we still do not know whether gravity is fundamental, emergent, quantized, or something entirely unexpected. It shapes the universe. It controls time. It binds galaxies. And yet it refuses to reveal its deepest nature. Gravity is the weakest interaction in the universe, but it governs everything. From the fall of a stone to the birth of stars to the fate of the cosmos itself.